All right, guys, this is the Physics First Test 1 review guide. That Test 1 has bugged me as I've graded and tried to find it. It's your first test, which is fine, but just to be sure, this is your Unit 2 review guide. I am going to read to you. You may type directly on this document or print it out and write on it before you turn it in. The Dropbox will accept Word files or PDF files or JPEG files if you upload a picture of your handwritten work. Please be sure to turn in the correct stuff. I do look at everything that you turn in and check it. Next, completion grade. Complete means you do as requested. Show your work. Just answers will not receive credit. That's not completing it. So please be careful about that. All right, this was a completion grade. You turned it in. It looked like you had tried it, had some answers. You got a 100. Those days are gone. Okay, I need to make sure that you master this stuff. I am going to help you on Tuesdays and Thursdays. Um, I need to see you show the work. So let me walk through this so some of you can turn this in and get credit. Right, we're going to follow the problem solving steps, show our work. Cam Newton can sprint 40 meters, number in a unit, in 55.79 seconds, right? Those are my givens. Meters is a distance or a displacement, 40 meters. Seconds, well, that's a time, 5.79 seconds. What's my unknown? Wants to know how fast. Well, what is fast? It's speed or velocity. We use the letter V for both of those. So my unknown is V question mark. All right, let's have this out. So if you will follow the problem solving steps, these problems become a little bit easier. D, V, and T. This is the only formula with V, D, and T. So I know that that has got to be it. V equals, I have to do it, change in distance over change in time. Substitute. V, I don't know it, that's my question mark. Change in distance, must have started at 0 meters, and he went 40 meters. 40 meters minus 0 is 40. Took him 5.79 seconds. Probably started at 0, right? So 5.79 minus 0. Right, I solve. So 40 divided by 5.79. Forty divided by 5.79. You notice this crazy number, 6.90846. There's 2 digits and 3 digits. So I'm just going to round to 2 digits. 6.9. Notice meters per second. And I check myself. That's a velocity. Velocity of the variable is measured in the units, meters per second. How far will a bird travel in 13 seconds, number in a unit, if it maintained a speed of 31 meters per second, number in a unit? Givens, seconds is a time. Meters per second, well, it's right there for me as a speed. We use the letter V. I know what I'm looking for. Well, this is far, right? And far is a distance. So get to know these words. Fast, they're wanting velocity, and far, they're wanting distance. Again, what's the only formula that has T, V, and D? Well, this one. Change in distance over change in time. I substitute, oh, wait a minute, I'm looking for D. I need D by itself. I'd like you to do algebra, right? So V, whoops, equals change in distance over change in time. I want distance by itself, so I'm going to multiply both sides by time. What I do to one side, I do to the other. So d is v times delta t. D is velocity times change in time. Of course, another way to do that is I'm trying to solve for d, and so it's v times t because they're beside each other. They're beside each other. The total change in distance is however fast he ran times whatever time it took him. Right? Oops, I meant to write that down there, didn't I? All right, so let me just do this. Velocity is 31 meters per second. Time is 13 seconds. I solve. Oops. 31 times 13 equals 403. Now by rights, there's two numbers. I should only report two numbers, so it should be about 400. But we'll just leave it at 403. But you might see 400 on a test. 403. Hey, look at this. Meters per second times seconds. Seconds is on the bottom and on the top. They cross off. I'm left with meters, and that is a distance. So that worked out very well. Number 3, Ian walks 10 kilometers to his best friend's house, then walks 0.5 kilometers. Oh, I've got two distances. I'm thinking through my problem already. He then makes a 2.5 kilometer walk home. The entire walk took him 3 hours. What is the average speed in kilometers per hour? All right, so what am I given? Well, his first distance, we'll just put D1, is 2 kilometers. His second distance is 0.5 kilometers. It's nice, it doesn't just tell me that he walks home and I have to figure it out. It actually gives me the number, 2.5 kilometers. So his distance is 2 plus 0.5, and he walks all the way back. So the total distance is 5.0 kilometers, right? I'll make a note that he's back home. His displacement is 0. His distance is 5 kilometers. The entire walk took him 3 hours, number of units, so that's another given. T equals 3 hours. Well, what are you asking me about? What is his average speed? Speed, fast, those are represented with the letter V. How fast is he going? Formula. Again, V dt, so V equals a change in distance over the change in time. I substitute. V is a question mark. His total change in distance, 5 kilometers. The time it took, 3 hours. They want the answer, by the way, in kilometers per hour, so this is cool. Kilometers per hour. I've set this thing up right, I'm pretty sure. Right? So 5 kilometers in 3 hours. It dawns on me, I don't know how to clear my phone. All right, 5 divided by 3 equals 1.666666. Goes on and on forever, but it's 2 significant digits or 1 significant digit, just 1 here. So I might be tempted to write even the number 2, but we'll go ahead and we'll put 1.7. Right? I'm going to round up, right? That's above 5, so I'm going to round that 6 up to 7. In kilometers per hour. The truck speeds up from a velocity of 6 meters per second to 15 meters per second. I note I have 2 different velocities here. Okay, it gives me the word velocity, but meters per second is a velocity, so it's speeding up. in 4 seconds. What is the truck's acceleration? So I've got a couple velocities. Seconds is a time. I need acceleration. So given his first velocity is 6 meters per second. His second velocity is 14 meters per second. And that all took him just 4 seconds. Unknown, what am I looking for? Well, I'm looking for acceleration. It's right there, A equals. So what's my formula? Well, I have A, I have a couple V's, and I have a T. That's that change in, right? And you always subtract the last from the first, final from initial. Okay, so F and little I, or 2 and 1. Okay, it'd be good if you did that with velocity too. Whoops. A equals change of velocity over time. Did not start off at 0, so I have to look at both of them. V2 minus V1 all over T. Substitute. A, I don't know it. There's a question mark there. V2, my second one was 14 meters per second. My first one, he was already going 6 meters per second. And that took him 4 seconds. Now, notice the units, meters per second, or meters per second squared. That's acceleration, so I know I've done this correctly. 14 minus 6 is a positive number. Well, he's speeding up. His acceleration is positive, so that makes sense. Fourteen minus 6 is 8 seconds. I just wanted to show you the meters per second again. Push this up. So 8 divided by 4 is 2. Meters per second is meters per second squared. Acceleration is always meters per second squared. Or rather, I should say meters per second squared is always an acceleration. Number 5. The car starts from rest, right? Got to be careful. I'm pointing off the screen here. Fast is a velocity. Far is a distance. Speed, we use velocity. Here's another word we got to be careful of, the word rest or the word stop. How fast is rest or stop? Right? Let me pause and say its first velocity is 0. It's starting from stopping, from resting. Okay? 15 meters per second, another velocity, 2.5 seconds, a time, and I'm looking for acceleration. It's very similar to question 4. So initial velocity, just getting the word rest. Second velocity, time. What am I looking for? Acceleration. What's my formula? Well, acceleration is speeding up or slowing down or changing direction, right? We've talked about vectors since you did this sheet. Acceleration is a vector. So speeding up, slowing down, the magnitude changes or it's changing direction. Hopefully that makes sense. All right, delta V over delta T, but normally we start at 0. Substitute. A equals, well, my second velocity was 15 meters per second. My initial velocity was 0. I'm going to write it. Keeps me honest, keeps me thinking about things. 2.5 seconds. I solve. 15 minus 0 is a positive number. It should be positive. He sped up. It's a positive acceleration. 2.5 seconds. So just like I did last time, just to drive the point home, 15 meters per second divided by 2.5 seconds. Meters per second, or meters per second squared. The variable and acceleration's unit. So 2.5 goes into 15 6 times, right? And I'm going to put 6.0 because that has 2 numbers. This has two numbers, so I'm going to give my answer in two numbers. All right, a resident throws a bag full of trash over the balcony of their third floor apartment. What will happen to the acceleration of the trash bag as it passes the second and first floor? Right? I might have been tempted to add the word then, right, to show. So we'll draw a little building. Right? Resident throws a bag full of trash over the balcony of their third floor apartment. Don't know why they're doing that. They should be arrested. All right. What will happen to the acceleration of the trash bag as it passes the second and then the first floor? All right. Hey, y'all, I'm going to be really picky. I'm not sure how this was done before. It asks about its acceleration. Near Earth, acceleration is because of gravity, and that is negative 9.8 meters per second squared. That does not change. Its acceleration does not change as it falls. Well, what does change? Well, I throw it off the balcony. It's not going very fast. It's accelerating. So it's going faster. And before it hits, it's going even faster, right? Velocity is increasing. Displacement is increasing. They're both down. Okay? They're both down. But a tricky question, I've seen this on multiple choice tests, okay? Acceleration doesn't change near Earth. It's negative 9.8 meters per second squared. So just be careful about that. It's a wording thing. All right. A high-speed digital camera captures a bungee jumper diving off a bridge. What happens to the distance between the jumper and the bridge in each picture taken? Well, here's my bridge. Here's my crazy bungee jumper. Okay. Well, he's accelerating, right? Gravity is pulling him down, and he's speeding up. His velocity is going faster and faster and faster. You go 10 miles an hour, you're going to travel 10 miles every hour. If you're going 60 miles an hour, you're traveling 60 miles in that hour. Kind of obvious, but there it is. So he's speeding up. So what happens to his distance? You guys have drawn these little dot structures. First, he's not going very fast. But then he goes faster and faster. He doesn't travel much distance in that first change in distance or change in time. The second one, a little bit bigger. Change in distance that third time, it's getting larger and larger, right? What happens to the distance? Okay, distance or displacement in this case, it's getting larger and larger because he's accelerating. His velocity is getting larger and larger. The velocity of the car reduces, keyword, from 30 kilometers per hour to 5 kilometers per hour as the car approaches a stop sign. Is this an example of positive or negative acceleration? Circle the correct answer. Well, the answer is negative acceleration. Let's go to our formula. Acceleration is change in velocity over change in time. They don't give us much information here, but the second one is 5 kilometers per hour. And the first one, he started off at 30 kilometers per hour. And we don't know the time. 5 minus 30 is negative 25 kilometers per hour over some time. Notice my answer is going to be negative. Okay? Please get used to using your formulas. They help you answer these questions. Number 9. A car travels at a constant velocity of 7 miles per hour. I just don't like that. Miles per hour for 1 hour. At the second hour, the car's velocity was 60 miles per hour. At the third hour, the car's velocity was 80 miles per hour. At what hour was there positive acceleration? At what hour was there negative? So I'm going to do time 1, time 2, time 3. So he's traveling at 70 miles per hour, traveling at 60 miles per hour, traveling at 80 miles per hour. I'm not sure about the wording of this question exactly, but the point is good. At what hour was there positive acceleration? Okay, positive acceleration, the change in velocity is up, right? A little bit more to the story if you take physics later, but positive acceleration, the change in velocity, it goes up, right? It's positive. It's up. It's positive. Negative acceleration, on the other hand, right? The change in velocity is down or negative, right? We had a negative example in number 8. So this is positive from hour 2 to hour 3, and this is negative from hour 1 to hour 2. He's decelerating, we say. That's negative acceleration. Before we get started, I just need to point out this is a distance time graph. This is a velocity time graph. Whenever you go to a graph, you're going to have to look very clearly to see what's going on. This gives us units and numbers. This one does not. You can make up your own as you're going to see, right? So the first thing you need to do is study your graphs. Answer the following questions using the distance and time graph above. What does the graph tell us about the velocity of the car? Well, in the second, right, at t equals 2.0 seconds, the velocity, or the distance, I'm sorry, is 5.0 meters. Think math, 2.0 seconds, 5.0 meters, right? That's the point right there. Let's just go out here to 6. In some second time I've chosen, 6 seconds. His distance is, let's check this out, up here, over 15.0 meters. Again, if you're thinking math, 15.0 meters. Hey, y'all, you don't have to write everything I write. I'm trying to teach and show you. Some of you will be more comfortable with this, and some of you will be more comfortable with that. Either one, maybe even just drawing so I can see what you were thinking. What does the graph tell us about the velocity of the car? Well, so far, nothing. Right? I've got time and distance. Okay, I do know it's not going 0, right? That's 6 seconds, 15 meters. So as I move along, I see that he's traveling. So what does the car travel about the velocity? Right now, there's a positive velocity. The change in velocity is positive. He's going from 5 meters to 15 meters. It's not negative. He's not getting closer and closer to 0. It's not staying at 10 meters away, some straight line. What is the average velocity of the car? Okay, well, we have to go back to our sheet. The velocity is change in distance over change in time. I'm going to do this 2 different ways. So velocity is change in distance over change in time. Let's go ahead and use my points. So the second one was 15 meters. And the first one was 5 meters. The first time I chose was 2, and the second time was 6. So second time 6, first time 2. So 15 minus 5 is 10 meters. 6 minus 2 is 4.0 seconds. So 10 divided by 4 is 2.5 meters per second. Notice that meters per second, which is a speed. So we've done something correct here. Okay, on and off the board. Okay. Well, this one's nice, and this was not true of the next sheet you did. One of the points could be 0, 0, but you need to recognize the fact that on this graph, 0, 0, okay, and sometimes we do put T0 or T0. At 0 seconds, the distance was 0. That's a valid point. So I could subtract 15 minus 0, 6 minus 0. And I'd get 15 over 6. Okay, I just want you to recognize that that delta means change in, and this one's nice only because it starts at 0. And that is not always true. Okay, if you'll note, check your calendar, or your calculator, 15 divided by 6 is 2.5. This is a nice straight line, right? I go over a second, he's gone 2.5 meters. I go over another second, he's gone 2.5 meters. You can kind of do slope in this fashion. Is the velocity reflected in the graph positive or negative? Well, it's positive. I think you already saw that before. He's moving away in some positive direction in the up here in that first quadrant, if you're comfortable with math. Okay, so it's positive. And notice second minus first. Second minus first always. Final minus initial. Final minus initial. I got a positive number. Okay, that's not an accident. That is positive. Is there any point on the graph where the car is not moving? Well, no, not at all. This is one nice straight line. Every second, he moves further and further away from 0. Okay? Moves further and further. At 10 seconds, he's now 25 meters away from where he started. There's no straight line here. All right, velocity. Now, I'm going to suggest to you that you think in units. I'll just put miles per hour. We're pretty comfortable with that. That hours there, I'll put hours here. And we'll go 1 hour, 2 hours, 3 hours, 4 hours, right? Let's go, I don't know, 20, 40, 60, speed double 80, right? You make up your own numbers. It might help you out to recognize the story that the graph is telling. Okay? Right, answer the following questions using the velocity and time graphs to the left. If each letter represents a car, list all cars which are decelerating, a negative acceleration. Well, the only one here is A. Okay? At hour 0, when we catch up with him, he's going 80 miles per hour. At hour 1, he's going about 60. At hour 2, he's going about 40. At hour 3, going about 20. And by the time the 5th hour rolls around, he's going 0. He's decelerating. That's a negative acceleration. Okay? Acceleration equals change in velocity over change in time. Let's play with my numbers just to show you something. In the 5th hour, he's going 0 miles per hour. In the 1st hour, he was going, let's just call it 60. So 1st hour, 5th hour, that's 4 hours. Okay? 0 minus 60 is negative 60. There's that negative divided by hours. Miles per hour per hour. Oops, I'm off the board again. Miles per hour squared. Meters per second squared. Miles per hour squared. Get used to these. Is an acceleration. B, list all cars which are accelerating at a positive acceleration. Well, conversely, that would just be B and D. They both started off at 0 in the 0 hour, and by the 5th hour, they have sped up. Notice that D has only gone up to about 20 miles per hour, and B is up here at about 60 miles per hour. So they're accelerating more than D. Okay. List all cars which have a constant acceleration. Well, let's just rule out C for a second. No acceleration. No acceleration. At the 0 hour, when we meet the guy, 40 miles per hour. 1st hour, 40 miles per hour. 2nd hour, 40 miles per hour. 3rd hour, 40 miles per hour. 4th, 5th, 40 miles per hour. He's not speeding up or slowing down at all. C, forgive me. C has constant velocity or speed, right? These are positive numbers, so positive's a direction, so velocity or speed. I know it's 40 miles per hour. All the others, these guys that we've just talked about, A, B, D, of a constant acceleration, whether it is negative or whether it is positive. Okay? All right. Please use your math. Okay? Find those points, right? I'm kind of scribbling along here. Find those points and tell the story. If you don't have points, write your own units, come up with your own points to answer these questions. Throw in your numbers if you're really confused. Just play with them. I didn't even do all the work. I never divided 60 by 4, but I saw that negative number I was looking for. Number 12, answer the following questions using the velocity and time graph above. So velocity, time. At what time was the car stopped? Well, what stopped? 0 kilometers per hour. So, well, right there at 0, it started. So at 0 hours, when it began, it was going 0. Way out here, 0.7 and 0.8. So from 0.7 hours to 0.8 hours, it's the only other time, just drawing this line across, that it's going 0 kilometers per hour. Everywhere else, notice if I picked any point along these lines, I would end up with some sort of velocity. At what time was the car maintaining a constant velocity? Those are flat lines. So at 0.2, he's going 60 kilometers per hour. At 0.3 hours, 60 kilometers per hour. At 0.4 hours, 60 kilometers per hour. These plateaus, right, this is not a hill. It is not a map. This is data points. Okay, he's going along possibly, probably in a straight line. He's just driving along in a straight line like these guys right down here. Driving along in a straight line. He's speeding up, constant, slowing down, comes to 0, speeds up, not as much, and has a constant again. So these plateaus on a velocity time graph are constant velocity. Look at these points. Okay, so constant velocity is 0.2 hours to 0.4 hours and 1.0 hours to 1.1 hours. At what time did the car accelerate? Right, so it's not clear here whether it's positive or negative. It just says the word accelerate. So from the last question, I have to do both. And notice it's positive, right? Because during this time, it's going 20 kilometers per hour. It's going 40 kilometers per hour. It's going 60 kilometers per hour. Travels along, not too long actually, and then he begins to slow down. He's now going 60, slowing down to 40, slowing down to 20, comes to a stop. He speeds up again. So there are 3 points that he's accelerating. 0 hours to 0.2 hours. Okay, a positive acceleration. 0.4 hours to 0.7 hours. He's slowing down. His speed is becoming less and less. Negative acceleration. And then very briefly here, 0.8 hours to 1.0 hours. He's accelerating. And I'll just plus, negative, plus. Positive acceleration, negative acceleration, positive acceleration. At what times did the car have a negative velocity? Never. These are all positive numbers. Okay? He did not turn around. He's going out there straight. So these are all positive numbers. There are no negative velocities. Careful, this is negative acceleration. But if you look at some points, that's positive 10. That's positive 30. It's positive 50. You can look at any points along here, and the velocity is positive. So he's never, ever negative. That'd be down here in the graph, right? Down to your negative numbers. Think about your math. All right. So these are Ticker tape dots is where these little dots came from. Every second on an old ticker tape machine, the pin would drop behind a car, right? Every second. So second pass hadn't gone very far. Second pass, second pass. So, oops, I'm pointing to the velocity ones, the distance ones. Second passes, notice what's happening about the distance between them. Okay, so it went far here in a second, and then it didn't go so far in a second. Okay, so that's the old ticker tape machine. And of course, now you guys know a little bit about vectors. What can we say about the velocity of each of the cars in the three separate diagrams above? So might have written this a little bit differently. There are three diagrams. Well, here we see the velocity is increasing. So it has a positive velocity that is increasing. Right? It's moving to the right. Here, what's going on? Again, I guess the velocity. So notice the vector is getting smaller and smaller and smaller. It's still a positive velocity to the right, but the velocity is decreasing. So increasing, decreasing. And notice these vectors are all the same size, right? The car is the same distance from each other. So this one has a constant positive velocity. They're all to the right, so they're all positive. Okay, just think about vectors and what we've learned. But it's velocity is increasing, it's decreasing, and it's constant. It's the same. All right, last page, and there's these ticker tapes again without the vectors. Which is true about the diagram above? Well, let's go ahead and look before we read the answers. There's a ticker tape, so every second that little thing falls. And notice it falls and it hits the paper again, and the vehicle has not gone very far. From the 4th second to the 5th second, it goes up, the ticker tape comes back down, the little pin comes down, and it's covered a lot of distance, right? So this thing must be accelerating, right? And again, it's to the right, 1 through 5, so some positive acceleration. Every second, it falls. So here, there's no acceleration, okay? The velocity is constant. The distance between is the same. The distance between has very much changed in that 1 second. That's what ticker tapes are all about. D shows 0 acceleration. Well, that's not true. And G shows constant velocity. That is true, but that's not true. D shows positive acceleration. Yes, going to the right, positive acceleration. And G shows negative acceleration. No, it's not slowing down. It's a constant velocity. That's not right. D shows 0 acceleration. No, we said it's speeding up. And G shows positive acceleration. It's not accelerating at all. I really hope D is correct. D shows positive acceleration to the right. It's going faster and faster. G shows 0 acceleration. Yes, good. D is the correct answer as I look at my ticker tape. All right, finally. You want to calculate the displacement of an object thrown over a bridge. Using negative 10 meters per second squared for acceleration due to gravity, what would be the total displacement of the object if it took 8 seconds before hitting the water? Well, what am I given? I get to use that for acceleration due to gravity. Took 8 seconds. Seconds is a time. My unknown is what would be the total displacement. So I'm looking down. These were displacement rather than distance. Still D. I don't know it. What is my formula? Better find a formula with A, D, and T. D and T, but no A. Oh, right. So here, G, right? Acceleration due to gravity. So this is the one I want. I don't know anything about velocities, okay? I have to recognize that A and G. So D equals 1/2 GT squared. Substitute. D, question mark, equals 1/2 -10 meters per second squared. Time is 8 seconds, and all of that is squared. All right, let me just do something just to be sure. I'm going to keep the 1/2. I'm going to keep the -10 meters per second squared. 8 squared is 64. S squared is S squared. Don't forget that. Notice S squared and S squared cross off. I'm left with meters, which is a distance. Yes. Right. -10 times 64 is -640, but I need half that. So it's a -320 meters. Why is it negative? Well, it asks for me displacement. If you ask me distance traveled, I say, wow, he fell 320 meters. If you ask me displacement, I need to know the place. I need to know the vector, and he fell down. He did not get in a cannon and go up. So -320 meters. Thank you all. I do want to see this work on your paper, and hopefully this will help you in the future.